Hello everyone and welcome to the ROS Navigation in 5 days course. In this video we are going to have a look at Unit 1, Basic Concepts. So what are we going to see in this unit? Basically you are going to have an overview of some of the main concepts that you are going to learn during the course. Yeah. So you are not going to learn anything very deeply, but you are going to have a general view, let's say, about what is the ROS Navigation Stack and what forms this ROS Navigation Stack. All right, so let's start. So what do you need in order to perform robot navigation with ROS? So let's say you want to start navigating a robot, but you don't know anything about ROS, anything about navigation, but you have one project and you want to make a robot autonomously navigate inside an environment. So what do you need in order to do this? What do you need in order to perform ROS navigation? Well, the first thing you need is a map, obviously. So the first thing is a map. This is like when you travel to another country, yeah, and you want to start moving around that country. The first thing you need is a map. Yes, because you need to know where the different places are located, etc. So in order to navigate, always the first thing you need is a map of the environment. In this case, in this simulation, as you can see, we have a cafeteria. So if I want to start navigating my robot here, I will need a map of this cafeteria. Yes? And this map is created during the mapping process. In the next unit we will discuss more deeply about mapping. Yes, but this is known in ROS Navigation as the mapping process. So let's do a quick demo here in order to see more or less how this works. So I'm going to launch this command here. ROS launch robot navigation gazebo gmapping demo.launch. Then I'm going to launch as well this command here in another web shell. Let's execute it. And finally, I'm going to launch this third command here. Excellent. So now what I'm going to do is to open the graphical interface, which will open a new tab. There we are. With RViz, yeah? So this is RViz. You probably already know this tool. Okay, so what's this? This is basically a visualization of the mapping process. So here you are visualizing how the map is being created. Yes? Let's come to this web shell here where we have launched the keyboard teleop, and let's move the robot a little bit around using this using the keyboard. Let me do this. Okay, so I'm going to move a little bit the robot around. Yeah, there we are. Let's increase a little bit the speed. Okay, I think it's enough, more or less. So as you can see, my robot is moving around the environment and it is generating the map of the environment. Yes, you will see later why this is gray, black. So these red lines you are seeing here are the readings of the laser. Yes, and these readings of the laser are being used in order to create the map. Okay, but well, I don't want to talk too much about this because this is just a demonstration of the mapping process. We will discuss properly this topic in the mapping unit. Okay, so this is a demonstration of how a map of the environment would be created. Yes, you will move the robot around the environment you want to map, and while you move the robot around the environment, the map will be automatically generated like this. Okay, excellent. So let's stop these comments here and let's keep on seeing what we need in order to perform ROS navigation. So the first thing we need is the map. But once we have the map, what do we need? We need to localize the robot on that map. Yes? So, for instance, I will say it again. Imagine you go to a city you've never been before. The first thing you will do is to get a map of that city. But the next thing you will need to do is to know where you are in that map. Yes? So this is very important because you can have a map, but if you don't know where you are in that map is completely useless. So you need to localize yourself in that map. So you need to be able to localize your robot in that map. And this process is known in ROS navigation as localization. Alright? Then let's have a look at the localization demonstration as well. So let's execute this new command. Again, there we are. We are going to launch the AMCL demo launch file. We are going to launch again the keyboard teleop here. And I'm going to launch RViz as well in this web shell. There we are. Very quickly and in very general terms, because we are going to discuss this properly in the localization unit. But what are these green arrows you see here? Basically, these green arrows are possible positions of the robot. Yes? Are guesses of where the robot could be. Many guesses of where the robot could be, and they indicate the position and the orientation as well, which is it's indicated in the direction of the arrow. Yes, so these arrows have an orientation and have a position associated to them. And each of these arrows you see here is a possible position of the robot. But as you can see, this is has a lot of error. It's not accurate at all. But wait a second, let's do one thing. Let's start to move the robot around, because there are other things that are not okay here. So the laser readings are not related to the map as well, for instance. But well, let's do one thing. Let's move the robot around as we did before, using the keyboard teleop. There we are. So let's start moving a little bit the robot around. We are okay. So what is happening here? As you can see, the arrows have concentrated a lot. So by using the movement of the robot and the readings of the laser about its environment, the most probable guesses are the ones that are concentrated in one place. Yes? So the more you move the robot around, the more information you will get about the environment, in this case by using its laser. So the more accurate the arrows will be, and all the possible guesses that are wrong are eliminated, are erased. Yes? Very interesting, but yeah, let's wait until the localization unit in order to learn more about this. But for now, yeah, keep in mind this. So localization is done through guesses that the system does about the position. Then these guesses are evaluated and are eliminated if they are considered wrong. And this is done by moving the robot around the environment in order to get more information about the environment. Yes? Alright, so let's stop this demonstration. We will learn more about localization and how this process works in the localization unit. But for now, let's leave it like this. Then, okay, what's the next thing you will need for performing ROS navigation? So first, we need the map. Then we need to be able to localize our robot in that map. Then once we have this, we can send goal locations to our robot. So you can say to our robot, hey, go to that position in the map. And then the robot should autonomously navigate there. Okay, so let's try this. Let's test this. And for that we have this third demo here. So again, let's execute the commands that appear in the demonstration. So let's launch this one first. Let's launch RViz as well. In this case, we are not launching the keyboard teleop, of course. Great, there we are. So we have our system again like this. Then now I'm going to show you a trick to help the robot localize itself in the map. Yeah, this is done by using this 2D pose estimate tool. So with this tool, I can tell to the system more or less where the robot is. Okay, so let's have a look here in the map. So the robot is more or less here, and it is in that direction because we have to specify the position and the orientation of the robot. So I would say that more or less regarding the map, the robot is here. Okay, so let's select this 2D pose estimate tool and let's place it where I think more or less the robot is and its orientation, which I think more or less it's something like this. Okay, so I will leave it like this, and then automatically all the position guesses move to this point. Okay, so now I have more or less localized my robot. As you can see, the laser readings are not perfect, they do not match exactly with the map, but well, this will be corrected while the robot moves, so don't worry. Okay, now what I want to do is to send a goal position to the robot, and this is done by using the 2D nav goal. So I can come here to the 2D nav goal and select a position and orientation I want my robot to go to navigate to. So for instance, I will tell my robot to come here. So let's see what happens, and as you can see, the robot starts to move autonomously there. You can see it in the simulation, how it is going to that goal. And while going, the matches in the lasers are adjusted to their correct values, and the localization as well eliminates all the wrong guesses. Yes? So it makes the localization of the robot much more accurate, because while moving I'm getting data about the environment. Alright? So as you can see, now I'm able to send goals to the robot in order to make it go to any position in the map. Yeah, for instance, let's make it go back again to this place. Yeah, there it is. It creates a plan, which is this green arrow. Okay, so don't worry, this is just a general view of the ROS Navigation Stack, but you will get much more into it in the different specific units, yes, for mapping, localization, path planning. So don't worry, this is just a general view, so you can start seeing and working with some things. Okay, so great, yeah. So now I am able to navigate autonomously through the environment, yeah. But you will say now, okay, but what happens if something that is not represented in the map steps into the map? So for instance, let's say this is a real environment and a person comes to this cafe and starts walking around here. What will happen? Because this is not represented in the map, right? Okay, so let's have a quick demonstration about this as well. So let's stop our launches and let's have a look at this. So we are going to launch this new command. There we are. We're going to execute this command here. Yeah, well, those errors don't matter. So I'm going to execute this command, which will spawn a new object into the cafe. So let's execute this command. And as you can see, a new object, a new block has spawned here into the environment. And this block is not... Okay, let me launch RViz. Okay, let me launch RViz, 1 second. There we are. So as you can see, this object is not represented here in the map. It doesn't appear here. So what will happen if I try to navigate through that object? Let's check it. So first of all, I'm going to localize my robot again, which is, yeah, okay. So it's more or less here, and it is facing that direction. So let's, okay, more or less, I would say it is here, more or less, okay? So let's place it here. There we are, okay, quite accurate, as you can see. So, well, yeah, so my my object, my new object I have spawned into a simulation doesn't appear in the map. So let's do one thing. Let's navigate a little bit the robot so it localizes better. And now what I'm going to do is to send a goal around here. So I will force my robot to go past the point where I have placed my object, okay? So I will make it go around here. So let's see what happens. Okay. You will go more or less here. Okay. So as you can see, the robot, it is avoiding the obstacle, despite it is not shown in the map, but it is being shown here in the laser readings. This red line represents the robot, how the laser beams are hitting the obstacle. So despite the object is not represented in the map, the robot is still able to see this object thanks to the laser. Yes? This is called obstacle avoidance. Okay? So yeah, let's finish this demo here. I don't want to talk too much about these topics because you will discuss them in their specific units. So let's do just a recap, a summary. So in order to perform ROS navigation, you need first a map. a map of the environment you want to navigate, of course. Second, you need to be able to localize your robot inside that map. Yes? Then you will need to be able to perform path planning, to calculate plans, to go from one point to another in that map while avoiding obstacles. Yes, this is called path planning. And finally, you need to avoid obstacles that are not shown in that map. Okay? Which is known as obstacle avoidance. So this is the 4 key points in ROS navigation. Okay? And they will be discussed in each of the units of this course. So the second unit, you'll discuss about mapping. The third unit is dedicated to localization. And the fourth and fifth units are for path planning and obstacle avoidance. All right? Okay, excellent. So yeah, let's delete our model by using this command shown here. There we are. And yeah, let's keep moving. So another very important thing, which is not directly related to navigation, but it affects a lot in navigation, is robot configuration. How your robot is defined. Yes, this is extremely important for navigation to work properly. Yes? So how the robot is defined, how the robot is configured, how the robot is described. So I am talking about URDF files. Yes? URDF files are the Unified Robot Description Format. Yes? URDF files are the files that describe how this robot is. Yes? All the parts, all the links, joints in case it has joined your robot. Yes? But the URDF file defines who is your robot. Yeah? And why this is so important. Here you have an example of a URDF file. Yes? The joins, links. Then why this is so important? Okay, so if we have a look at this section, if we have a look at this section of URDF file, this section of URDF file is from this robot, yes? So here, it is defined the laser, yes? And it is defined where the laser is placed related to the robot. In this case, it's related to the base of the robot, which is this base link, okay? And this is very important because you need to know exactly where the laser is placed in the robot. And you need it, for instance, for mapping, for the mapping process, yes? You need that your laser readings are accurate in order to build a proper map. So this is crucial. If you say, for instance, that the laser is, I don't know, in another place of the robot, if it is not well configured, if it is not well defined, the readings that this laser does will not be correct. So the map will not be accurate. And with a wrong map, navigation will not be good. Yes, this is quite obvious. So that's why robot configuration is so important. In this course, we are not going to talk about how to build URDF files. We are not going to get into this because we will focus more in the ROS navigation packages. But there are other courses in Robotics Academy, like how to build URDF files, that you can have a look at them if you are interested in this topic, okay? But in this navigation course, we are not going to talk about URDF files and robot configurations, okay? So yeah, you have to just keep in mind this, that the robot configuration is very important in order to be able to do a proper navigation, okay? Excellent. So let's continue having a look to these notebooks. Okay, yeah, so basically we have the navigation stack, yes, which navigation stack is a set of ROS nodes and algorithms which are used to autonomously move a robot from one point to another. So use it to navigate a robot, okay? Then this set of ROS nodes and algorithms are the ones that you have been using in the previous demonstrations, yes? So this is something that ROS already provides. You just have to use it and configure it in the proper way, in the way that you require for your robot, okay? But all of these packages that allow you to create maps, to localize the robot, to calculate paths, to do path planning, all of these algorithms, nodes, packages are contained in what is known as the navigation stack, okay? And the main objective of the navigation stack, the main objective of navigation in ROS is to move a robot from a position A to a position B without crashing with any obstacle or get lost in the process. Okay, so this is the main objective of ROS navigation, of the navigation stack. Then, for being able to use this navigation stack, there are some hardware requirements that your robot should accomplish. Okay. For instance, here we have three. Okay, so the navigation package will work better in differential drive and autonomic robots. Okay, and the mobile robot should be controlled by sending velocity commands in the form x, y, linear velocity, z, angular velocity. Yeah, so this is the structure basically of a twist message. Okay, the twist message you probably have used it a lot of times. Yes. So the robot we want to navigate should be controlled by sending velocity commands in this way, yes? X, Y as linear velocity and Z as angular velocity. Also, and this is very important, the robot should mount a planar laser somewhere around the robot, yes? The place, it doesn't matter, but should have a planar, a laser somewhere, okay? And this is to build the map of the environment and for localizing the robot. Okay, we have seen a little bit of this in the demos, but you will get deeper into these concepts in the following units. Okay, and finally, the performance of their navigation stack is better for square and circular shaped mobile bases. Okay, it makes everything easier and work better. Yes, so these are some requirements that you should take into account when you want to start navigating a robot. Okay, then here we have the official diagram of the navigation stack, which is shown in the ROS wiki. Okay, and I am showing it because at this point probably it's very confusing to you. There are a lot of concepts, yeah, a lot of boxes, a lot of things connected, and you probably don't understand much of this. But I want to show it now because while you advance through the units, this diagram will start to make more sense to you. Okay? So for now, let's just focus on these four blue boxes. Okay? We have these sensor sources, sensor transforms, and odometry source, which are things that we provide to this general block. And then we have one, which is this base controller, yes, that we receive, let's say, from this main block, which is the move base block. Okay, so let's have a look at these four boxes. What are these? Okay, so first we have the odometry source. The odometry source is the odometry data of the robot. Yes, which basically usually this is given with wheel encoders. It can also be with an IMU, with a Kinect camera, for instance. But this the odometry, we need to provide odometry to the navigation stack in order to work properly. Okay, so our robot needs to provide odometry data. Okay, this is also a requirement for the navigation stack to work. Then, sensor source. This is related, for instance, to the laser. Okay, and this is mainly used, as we have said before, for localizing or for creating the map. Okay, so these are two things we need to provide to the navigation stack in order to be able to work. Okay, so we need to provide odometry data of the robot, and we need to provide some sensor data, for instance, laser data. Okay, then third, we have these sensor transforms. Okay, it is here. Sensors, you have seen odometry source, sensor source, and we have sensor transforms. Okay, so this is the configuration of the robot. So how your sensor is configured in the URDF file, okay? And how you are defining your sensor referenced to a common frame. Usually it is the base link, which is the base of the robot. Yes? So we need to provide odometry data, we need to provide laser data, let's say, and we need that this laser is properly configured and properly referenced to the base of the robot. Okay? And this relationship between the robot, the base of the robot, and its sensors is defined in with transforms, yes? With the TF topic. Then finally, we have this base controller, okay? Which we have it here, okay? And the main function of the base controller is to convert the output of the navigation stack, which is a twist message. You already know this message, probably. So the base controller transforms this twist message that the navigation stack will provide to us into a real movement of the robot, yeah, into command velocity commands for the robot. Okay. Well, don't worry. This is a lot of. If this is a little bit confusing at this point, I know it's quite a lot of new information, but don't worry. Yeah, remember that this is just a general view, and you will. I'm sure that everything will make more sense while you advance through the different units of the course. Okay? Excellent. So yeah, we are almost done. Here you have a small exercise in order to check the different topics that are related to the odometry, the sensors, the base controller also. Yes, you can do it. You can pause if you want the video and do it in a moment, as you please. I will continue with the explanation. And I'm going to talk about now the move base node, which is probably the most important node of the navigation stack. Okay? So the main function of the move base node is to move the robot from a position A, let's say, from its initial position to a goal position or position B. Okay? And of course, there are lots of processes inside here that interactuate in order to accomplish this. Okay? But the main function, objective of the move base node is to make the robot navigate to a position A to a position B. Alright? Then some of the packages that are linked to this move base node are these ones, for instance. This is just for you to know them, okay? All of these will be explained in different units, okay? But now this is just to introduce these concepts, okay? So inside this move base node, you will find, for instance, a global planner, a local planner, rotate recovery, clear cost map recovery, and cost map does 2D. Okay, these are different packages that take place inside the move base node. Okay, And this has, here we have other packages that are also linked in some way with the MoveBase node. For instance, the map server, the AMCL, and the gmapping. Okay? Yeah, don't panic. As the notebook says, don't panic. I'm just introducing some concepts, yeah, so they sound familiar to you. All of these will be explained properly in following units. All right? And yeah, let's do a summary to finish this first unit. This is a diagram I have created, which simplifies a lot the diagram of you have seen previously. Yes. So basically, how this whole ROS navigation works. Okay, so we have a move base node. Yes. And we need to provide to this move base node odometry data of the robot, transforms of the robot, and laser data. Okay, this we need to provide it to the move base node. Yes? Then we also need to create a map and to be able to localize our robot in that map. Yes? So all of these are things that we need to provide. Yes? These ones are things that we provide, the robot provides directly, the odometry, the transforms, and the laser. Yes? And these are things that we will need to generate using some navigation packages, okay? The map and the localization. But all of these, we need to provide it to the move base node. Then once we have this, we can send a goalpost to the move base node, and the move base node will give us as an output the proper velocity commands in order to move the robot from the current position it is at the moment to that goal position while avoiding obstacles, of course. Yes? So this is the main structure and the general idea of how this ROS navigation stack works. So yeah, that's it. I know it's a lot of new information, but keep calm. Don't worry, step by step, unit by unit. Everything will make more sense while you advance through the different units, okay? So yeah, that's all, and see you in the next unit. Goodbye.